Okay, so my name is Andrew Kent. Some of you may already know me. So this is a presentation that I think has probably come up more than once, and because almost all of us use Git for our version control. It's the versioning system which is pretty much dominating things. There were a few holdouts. I think Mozilla, for example, is still partially on Curelet, but my understanding is that they're migrating away. Canonical was using their own system, Bazaar, but I think they're doing the same thing. They're slowly migrating away from Git as just more and more people keep using it, and they find their developers are are just doing Git repositories. So it is slowly taking over everything. So what I'm going to cover is a very brief overview of how things work. I'm going to try not to go into too much detail, just because it would be very easy to disappear into all of the detail. I'm going to try to give enough to give a brief understanding and happily answer any questions. And then I'm going to go into an example of a workflow where we'll sort of touch on a whole bunch of commands. So hopefully that will be useful. And again, any questions, if I do anything, sort of what my plan is, if I'm going to go through these steps, I will point out things and sort of try to describe what's happening and ask any questions of something doesn't make sense or you're wondering why I did something a certain way, and I can try to give some background detail on it. So one thing I thought that I wanted to show was I've used a whole bunch of different versioning systems. So I did CSV when I went to university. I probably used a little bit of subversion when I was in university. I did subversion at work. I used Bazaar at one point for versioning a Drupal configuration. And then I started using Git, and I haven't used anything else for quite a while because it's really good. Similarly, I've started to use Git for other things as well. So Git versions more things than just my software. Again, it's the versatility of the tool, that it's very simple and it can hold a lot of data for you. So CSV and subversion are probably the two things that are most familiar. And the way that they work is very centralized. So you can have situations where you want to do something, you want to do a check-in, you want to do a merge, you want to do a branch, and you've got to talk to your central server in the middle. So the problem with that, sorry, is this reasonable out of this? Am I not getting it? Good? All right. So that works reasonably well. It works okay on small teams, but the problem you can get into is a lot of your operations then depend on how slow your network is. Depend on if you have network, and you also have to coordinate all the time with the other people who are working on your server, because you always know that the next command you do could be affected by something that somebody did on the server, because your commands are touching the central server all the time. So this works okay, but it doesn't work great. Now, you can have, but if you do a more decentralized flow, things get a little bit easier. And they also get more complicated. So this is the part where Git is very, very simple in some ways, but more complicated in other ways. And one of the things I'm going to cover in the commands workflow that I go over is actually some of the things that I do to kind of simplify things and not make use of some of the power of Git all the time, just so that things are easier to understand. So in this case, you can see you've got one maintainer and two contributors. And you can see the arrows are showing you where they're communicating. So you can see, so imagine that each of the laptops is a developer's workstation, and each of the server machines is the actual central repository the place where the developer is publishing their code. So that you can see the laptops have bidirectional arrows that only talk to their own servers. So it means that the servers don't have to worry about accepting things from other places. They know, I'm just talking to my one developer. They're the only one who does writes to me. But then, the So that then the contributors will pull things from the maintainer. And one day I will buy myself a laser pointer. So the contributors will pull down changes from the maintainer, and they'll do so independently. Each time they do that, they've got their own copy. So when they're doing things, nothing that the maintainer is going to do will affect them. They're isolated until they decide not to be isolated, until they pull down more changes from the maintainer. And they can then push things to their public server. And again, they're the only ones who have control of that, so they are the only ones who are doing updates to that. They don't have to worry about anybody coming in and stepping on their work. But so the question is, how do you get the part where, say, contributor 2 has done a bunch of work, and now they want to push it upstream because they want the maintainer to integrate that? So we know that maintainer 2 can only write things to her own server. So she sends her commits, she sends the changes that she's made up to her server, sends a message to the maintainer and says, hey, I've got changes, can you please come and look at them? And in the Git world, this is called a pull request. So it's saying to this maintainer, I have some changes. I would like you to integrate them into the mainline piece of software. Please read off all my changes and consider merging them into your own repository. So that means this server just has to publish. This doesn't actually have to allow the maintainer to write anything back to the server. So it has the potential to make those servers very, very simple. They're not always very, very simple because in a lot of cases, services like Bitbucket or GitHub or GitLab kind of pretend away some of the decentralization to make things easier to understand. But underneath everything, this is how it works. So you could have, parts of this can operate on the same machine. For example, if you go to a web interface and edit a Git repository, it's actually like you're doing the editing on the machine, and then it's pushing the changes up to the repository that all exist on the one server. Does that make any sense? Okay. So this, as I said, this is the part where if you're not careful, it can get more complicated. It can get a lot more complicated than just everything gets pushed up to a central server and gets pulled down from one central server.
So how do you know contributor 2 is working with the 1?
You don't.
So the 2 guys would do the same thing then?
Yes, exactly. So the question was, how does contributor 2 know what contributor 1 is working on? And in the context of Git, you don't. They're totally separate. They could be working on the exact same thing, and there's nothing within the Git protocol that would stop them from doing that. And there's nothing within the Git protocol that will communicate that that's happening. So that would be something, that's where, say if there's an open source project, it would be something you put on the mailing list and you'd explain, I'm working on this certain thing. If you were working with one of the centralized servers, you would potentially post a pull request early to, describe this is the work that I'm planning to do, and then eventually it will be published in your pull request. But yeah, within Git itself, contributor 1 and contributor 2 could very easily be working on the exact same thing. And if they weren't talking to each other, they wouldn't know.
So then it's up to the maintainer to resolve those problems?
It can be. It can also be up to the contributors. So for example, Bob's comment was that it was asking so if contributor 1 and contributor 2 are each working on the same piece of code, the question was, who will be the one that tries to figure out how those two pieces of code go together and to resolve any conflicts? So it could be the maintainer, because the maintainer could take both the pull requests and try to merge them on her own copy. But the maintainer could also say, contributor 1, I've taken your code. Awesome. Pulled it into the repository. Contributor 2, your pull request will now not merge without conflicts. Please resolve those conflicts. And that's where contributor 2 could then be the one who either fixes it up by bringing down the new changes and doing their own merge, or doing what Git calls a rebase, which is effectively rewriting their own local history based on the latest up-to-date changes, and then sending that up as the new set of changes that they want to commit. So again, the answer is it depends, and it's really up to the maintainer that you'll have. So if you're on a project, you'll have some maintainers who will take on the job of, I will take anything, and I will figure it out. But then, that's probably not going to scale very well for a large project. So, as you got bigger and you got more contributions, you'd probably have more instances where someone says, like, nope, I will not consider your pull request until it's not in conflict and say and the tests run clean. Well, does that make sense? So part of the question, so I've just said that sort of all of these machines are all passing around versions of some code. So, and when I say code, really, primarily it's just text. So Git is mostly good at versioning and managing text. So it doesn't have to be code, it could be any kind of text at all. So these are the things that Git is actually passing around. So this is the part where Git is almost stupidly simple, but it also gets really complicated. It's all the parts at the bottom are very, very dumb, but you can put them together in ways that get really, really complicated. So this is a directed acyclic graph, and all that means is there's no loops in it. So that if you start from one point in the graph and follow an arrow, you will never go back to the place that you used to be. And in Git, each of the nodes in this graph represent a commit. So, say, you start off developing your piece of software up here, this is your initial commit, then you make some changes, you add another one, you make some changes, you add another one, then you decide, I'm going to do a certain feature, and I make a bunch of changes, and then it doesn't connect back to the original branch. This would be something like, say, I tried out something, and it didn't work. So I didn't bother bringing it back into the main line of my graph. Whereas this would be an example of, I made a bunch of changes, and then I merged it back into my graph over here. So I said, oh yeah, whatever was happening, whatever changes were happening when we were on this branch, this set of commits, they were good. I want to bring them into the main line of code. So the way that Git represents this is it's in its data format. Each of these represents the set of things that have changed. It's a tree of files and a hash. I think it's SHA-256. So it does a hash of the contents of the change, generates a number to identify the change, makes it cryptographically unique. And also, the change that I do and the change that you do will not have the same number, where not is, statistically not, but that's okay. It's good enough for us. So they have that. So you make a change, and each change points to the next set of changes. So when you want to display something, or when you want to get the latest versions, you are working your way up or down the graph in the appropriate direction. So one of the benefits that this gives us is first that it's easy to pass the commits around, and the second, and the next thing is one of the things that Git's fairly famous for is the ease of branching. So in this case, this shows part of the reason why branching is very easy in Git, because branches are really just tags on commits. So this can be, this is sort of similar to BTRFS, one of the presentations we've seen in the last few months, that it's using the copy on write idea. So Git can preserve all the commits that you've created forever if you want to, because when you add new stuff in, all it's doing is making brand new commits. And so when you make a branch, all it's doing is pointing at the commit you just made and saying, okay, that's this branch. So similarly, if I was suddenly starting to do some new work and I said, okay, I want a branch to do the new piece of work that I'm doing, it doesn't actually do very much. All it does is points a label for that branch at the current commit that I'm on. So it doesn't have to talk to the network, doesn't have to move around a whole lot of data. It's just changing a label. It's basically adding a branch to the list. It says, okay, this branch points to this commit.
If you're saving everything, every time you make a change, does it save everything every time it makes a change, or is it just a difference of what was there before and the new stuff is?
It takes the things that have changed. So in your commit, it's storing the files that have changed. Now, internally, it does have a packing format where it will figure out how to store that in a more efficient manner. But it's taking so like when it does the SHA, it's doing a SHA of the files that you've changed, plus the tree object to represent how those files are connected together. And I may very well be not getting the details quite correct.
So the actual stuff that gets stored isn't everything every time you change?
It's a diff. Everything is a diff.
Yeah.
Okay, everything is a
It's essentially.
Yeah, I don't know. I couldn't tell you exactly what algorithm they use, but yeah, it's effectively a diff. Like there is a Git storage format that does a bunch of clever, efficient things to try to store everything as infrequently as possible. So to store everything once as much as it can. And I guess maybe an example of that is that if you have let's see. So we have multiple branches here. This is the master branch, and we've got several branches off, and they share these commits over here. These commits are only ever stored once. So there isn't the branch, but this branch is not an extra copy of these commits plus these other commits. It's the pool of commits that Git is holding for you is all of these commits. It's got one copy of each of them. And the way that you know that like, this particular path is a branch is because you start from the label here and then step your way back through all of the commits in order to see what the full content of your branch is. Which is kind of confusing. Yeah, that was fun. Sometimes diagrams are good for Git, but sometimes you also just need to look at it a lot. More questions? So, we're going to move on to actual commands. So this is going to be a somewhat live demo, but I actually have a script that will execute, so I'm somewhat not a live demo. So the idea is I'm going to run it. We're going to try to step through all of the commands that I've set up. Anywhere where you have questions, let me know, and we can sort of step out of the script and look at things that don't make sense. Or if things don't work quite the way I expected them, we'll go through and talk about why. So, that didn't work quite the way I expected it. Alright, so, can everybody read the text on the screen? Is that big enough, or should it be a little bit bigger?
Bigger is better.
Bigger is better. Alright. Let's go there. Okay. Yeah, most of my commands will probably be a reasonable size. All right, so what I'm going to do is I am going to pretend to be a remote repository and a local repository. So we're going to flip back and we'll go back to this diagram. So I'm effectively going to pretend to be contributor 1 and her server. So the server is the remote repository, and remote repositories are always stored in what Git calls the bare format. So they commonly have .git as an extension that's on their name, and you create them. So you make a directory, you go into it. Git init is the command that you usually use for creating a Git repository, and --bare makes a bare repository. So what a bare repository means is that it's got the Git commits, it's got all of the Git underlying work, but it doesn't have what's called the working directory. So it doesn't actually have the files exposed in a way that you could actually go and look at them directly. And so the bare repository is generally used for your remote repository that you are sending changes to. So it's relatively simple. This is sort of all the underlying stuff that shows up. You have a branches file, so this is where you have your list of branches and the commits that they point to. You can put a description if you want, and you will mostly ignore the contents of this directory because all of the Git utilities will be taking care of this for you. So that's a remote repository, and the next thing we're going to build is we're going to make a clone of that repository. And that's going to set up our local repository. And the local repository is going to be the one that we're actually going to work in, and the one that's going to have files we can actually manipulate. So something to point out, you can probably see that I did git clone remote.git, which is just a file name, it's just the name of the directory, and local, which is just the name of the directory. So usually, to make this useful, remote.git would need to be a remote address. So that could either be an address, there's various protocols you could use, but it could very well be like an HTTP address where the repository that you want to clone has been published. But it can also just be another directory on the same file system that you're working on. So it makes it simple, makes it fast for me to demo it, and I don't have to worry about pulling it down from somewhere else. If we finish early and anybody wants to see, that could be sort of going and pulling a remote copy could be something that I could show to, but we'll all mostly look the same. So you run, so the git clone .git local command runs, lets us know it's cloning into the local directory. It automatically creates the local directory for us. Now, it gives us a warning that we don't have any commits in our repository. So that means the only thing that was existing on our remote server was basically all the Git infrastructure, and there weren't any commits. So if we look into the local repository, again, we see here's all of the same stuff that was in the remote repository, but now it's stuck it in the .git directory. So the .git directory is the directory that you're not going to see most of the time. So that's where all the details of Git hang out, all the things to keep track of things, but not what you're going to work with directly. So this is what the Git utilities will manipulate. And as you can see, it's approximately the same thing that was on the remote repository. And now the first thing we're going to do is we're going to add some files to our local repository. So we don't want to do anything fancy, so we'll just echo some text into one file, we'll add some text into the second file. And then we start to get into the place where Git can kind of get complicated, just because there are a few more steps than there are in some other of the more centralized repositories. So Git wants you to actually effectively to construct the commit that you're going to make. So that means that it wants you to add the changes into the commit that you're building, and it holds those in what it calls an index. So you do a git add file 1 and file 2, and then that puts those files into the index that's on your local machine, but it hasn't made a commit yet. So the idea being that, say, if you were working on a complex piece of software, you would be able to, say you're working on one main change, and then as you're working, you realize that, you find a bug in something else that's not directly related to the main change that you're doing, but it's, you need to change to continue forward. So because you've got the index system, you would be able to make your one fix, commit that into the index, add that to your index, make a commit, have it ignore all the other changes that you were doing, and then get the commit, so your commit would contain just that one change, and you'd be able to continue on with the rest of your changes and make them later. And I should have had a slide for that. I did a presentation about a month ago, and I started off with every time I asked you to imagine something, what that actually means is I forgot to make a slide. And I think that probably could have used some more slides. So maybe in the future. So in this case, it's very simple. We want to add all of our changes. So we add the 2 files that we just created, and then we run git commit. So this makes a commit, gives it a message of initial commit, because each commit comes with a description as well. We get this output from Git, so it explains to us that Git has given our commit this this fraction of a SHA. So the SHA is 128 bits long? 128? Yeah. But because they are so unique, they are generally unique on the first 7 characters. So Git will take the first 7 characters of your identifier or more, and will generally figure out what the right commits are. So in this case, it's telling us we've got our commit has been created with an identifier number that starts with E960950. Give a description of, or given a title of initial commit, and indicated that, telling us what's happened. So 2 files were changed, it's counting them as 2 insertions, and it's created 2 files inside the commit. So this is what the commit is. This is what the commit's going to look like. So then we can actually look at the repository. So git status will then tell us what's happening inside the directory and the repository. So it lets us know we're on the master branch, and the branch is based on origin master, origin being the remote.git directory that we pulled from when we did the original clone. And when you do a clone, so upstream versus origin are probably a complicated detail that we shouldn't get into at the moment. But you can make your upstream and your origin different. So that can be useful if you want to push into, or if you want to pull changes from upstream. So if you are contributor 1, you can count your own server as origin, and that's where you push your changes to. But you can count the maintainer's server as origin, and that's where you pull new changes from. So, for example, as contributor 2 contributes things, contributor one wants to keep pulling down the latest changes that have happened to the central software so they can account for them and the changes that they're making. So that's just that. So the other thing that you can see that if there were still changes that we had made that we had not committed or that we had only put in that were either in the index or just on the file system, this would tell us about it too. And then we move on down to looking at more. So we see the next command we're doing is git log. I've included no pager because normally what git log does is it brings it up in less or whatever your text pager is, so you can actually scroll around in your log files. But I didn't want that because I wanted it to just print out to the screen. So what the log does is it gives you the list of all the commits on the branch that you're currently on. And you can tell it to look at other branches too, but in a very simplified version, it just gives you the list of all the commits of your current branch. So this looks at our current master branch and says, you have one commit. It's got the address that starts with what we saw before. It was created by me, created on this date, and it has a description of initial commit. So that's the only thing that's inside our branch. And the only thing that's inside our repository right now. Questions? Oh.
How do I see what the contents of that one commit were?
You skip outside the slides. So, demo directory is the directory where I have everything created. You can see remote.git is there, that's our remote file, and local is the repository that we were just committing into. So when I can go into local, I see my two files there. One second. Okay. So for information, this extra stuff is from a shell called ZSH, which is really awesome normally, but is less than awesome when you don't have a lot of screen real estate. So I'm going to turn some of that off and I'm going to go into bash. So you can see I've got file number 1 and file number 2. Those are just the two files that I created. Those are just regular files on this. Do git, the full version. So git status tells me all the stuff we saw before. Git log shows me the message we saw before, but in the pager, so this is in less, so if I scroll up and down, if I had more commits, I'd be able to see more of them. And then I can do git -u, and -u is the command to ask for a unified diff. And that's going to give me a diff of each one of my commits. So then I can see what's actually changed in that commit. So I've got a diff that tells me, so if I changed file names, it would tell me that I changed file names. In this case, it's telling me that I added this as a brand new file, and it's telling me for each one of them, I added a single line to each of these files. So this display would have the same, you'd see the same things that you'd see coming out of any other diff program. So there could be lines that were ignored, lines that were added that would have pluses, or lines that were removed that would have minus signs behind it. So this can get, so this is really this is close to the simplest commit that you can have. This can all get a lot more complicated, and there are a lot more tools for looking at things, and there are more arguments that you can add on to log to give you different things, to look at different sets of files, to display in different ways. So there's a lot more that you can dig into if you want to. So we created that commit, and what we now want to do is we want to push that commit back up to our main repository. So this would be the step you would be doing either because you want to publish the code that you want to do, or you just want to keep a safer copy on your server. So you're in the process of doing some work, and you say, okay, I've got a copy of it on my laptop, but my laptop walks around with me, I could lose it, it's one hard drive, all the things might go away. So I'm going to push the changes up to my server and keep a safe copy for me. So git push is the very simplest expression of that. And then it tells you, again, a bunch of information you can mostly ignore when things are going well about what it's doing. And it's just letting you know that it's counting the objects to be sent, doing some compression, writing them out, and sending them up to the server. And it lets you know, so down here, it's letting you know that it is sending changes from the master branch that's in your local copy to the master branch that's in the remote copy. So now this would mean that someone else could go, well, let's do a demonstration. So we'll come back out, we'll look in the directory where we've got local and remote.git. I can now do, I'm just going to make my font slightly smaller so it actually pushes my command line onto the next line. Or slightly larger. There we go. So, local and remote. So if you'll remember, when we cloned the local originally, remote didn't have any commits in it, so we got an empty remote. But now we've pushed up one commit into remote. So pretend I'm contributor number 2. And I go back, I say, okay, I'm going to clone remote.git, and I put it in local 2. So for local 2, you notice I didn't get the message about having an empty repository. And if I go into local 2, I've got the files. If I do a log, I'll see I've got the same commit. And I'll see that it's got the exact same identifier. So, now we're going to continue going through changes on the local repository. So we've done a push, so we've got one commit in the repository, we've pushed it up to a remote. And now we're going to start our actual development workflow. So I guess branches have become, so as people have realized how easy it is to make branches in Git, they've become more and more used. So in other centralized version control systems, branches were more expensive to make because they weren't just a pointer or a commit somewhere. They actually had to do stuff on the local machine and stuff on the server. So if you went to make one, it could take a while for the computer to just kind of think about how it's going to rearrange things to make the branch and copy around data appropriately. With Git, it doesn't do that. So you do git checkout -b to tell it you want to check out a brand new branch, and give it a name, and it runs almost instantaneously most of the time. So the fact that this is so cheap means you can make branches pretty much all the time. So whenever you start to do some new piece of development, you can make a branch. And that gives you the extra benefit of isolation. And we'll actually go through like a possible scenario where that isolation can come in handy. But so as soon as you make the branch, you've now got basically like a separate workspace where you are working and you are in control of the changes in that workspace. So you will be able to bring in upstream changes when you want to, you will be able to push your changes up when you want to. And you can also sort of pause your development more easily and switch over to something else, which is what we're going to show. As I said, the command we ran to get that was git checkout -b feature 1 to say that we want to be on feature 1 branch. Git will tell us switched to a new branch named feature 1, and then we run the git status command again. And now it tells us that we're on branch feature 1, whereas previously we were on the master branch. So, to go back to a picture, if you think of, so this is the line down the middle is our master branch. And if we imagine that we've reached this point, and now we're starting one of these chains. So we've started off a new branch because we're going to we're going to do some new development. So what I have found, and again, so going back to the branching being very cheap, I have found this has been one of the things that you should, my advice is to do all your development in a separate branch. That every time I haven't done it, something has happened that I've gotten into trouble and I've kind of had to get myself out of it in some way because I've either I've had to fix conflicts and changes that have come down, or I've just had to resolve things that in a way that wouldn't have happened if I had just sort of done what I usually do and started a branch. So even for very simple changes, like things where, I'm going in to change one line in one file, or I'm pretty confident that I'm going to be changing one line in one file, I will still make a branch because I've had it happen enough times. I think it's going to be one line in one file, but then it turns out it's this and this other thing, and then it all gets more complicated, and I may end up having to put it into a branch anyway, whereas if I just done it to start with, life was easier. And the cost of making a branch at the beginning is relatively small, so it's better to just do it. So, we'll start with the branch, and now we're going to add stuff into it. So, we do the same kind of thing to add an extra file. We just echo branch 1 into the file named branch 1. And now we're going to do a little bit of a shortcut. So, the git add command, where we previously used to explicitly add file number 1, file number 2 into the index, you can also tell Git that I just want to add everything. So it's either, you can use --all, or shorthand it with a --A, and it will just go and take all the changes, all the new files, and add them into your index. So that can be very useful just for not having to go and repeat, like to have to write out all the file names explicitly most of the time, when you have a simple change where everything you've done you just want to commit. So at that point, we've added it into our index, and we do the same thing we did previously. We make our commit, we give it a message. This is the first commit in our first branch commit. And we get the same kind of thing. It's telling us inserted one line, changed one file, and created this new file, branch 1. And then we'll do the same thing just to make 2 files and create them in 2 separate commits. So each commit can contain any number of changes. So generally what you are doing is trying to create commits which tell the story of the changes that you made. So in this case, I'm saying there is something about adding this file that's a thing by itself, and I want to give it a name and possibly a description. But adding the branch number 2 file is a separate thing. So, for example, if you go back to if you take the example that I said before of you're working on a certain feature, but then you find a bug in some of their code as you were going. When I used to work at CSV, I would find you just take all that and just put it all together into one big commit. And then somewhere in the commit description, you have to explain, this is my commit to add this feature. Oh, but by the way, it's also got a a bug fix for this, and a bug fix for this, and a bug fix for that I found as I was going through the code. Whereas in Git, in Git you could still do that. You know, your maintainers might be angry at you, because it will make it harder for them to know what you're sending them. But what you can do instead is to make each of those separate things. So you'd make one commit for the first bug you found, one commit for the second bug you found, one commit for the third bug, and then one commit for your actual feature change. And then someone reading through your history afterwards would be able to look through and easily see, oh yeah, I see, okay, the first thing they did was this, the second thing they did was this, the third thing they did was this. And which we can see here. And I'm actually going to hop over and get the log. Go back to local repository. And just go to full screen. So you can see we've got our initial commit. ID is still exactly the same because we haven't changed that commit. And we got our second commit and our third commit that have their own identifier, their own date. Got my information as the person who created those commits and their own description. So we'll say the story is we just made the first change that we wanted to do for our new feature. That was the first bit of the thing that we were going to develop. Then we get started on the next step. So we echo some stuff into a file. We do git status. And remember, so the changes we just made haven't been checked into the index, haven't been made into a commit. And now git status will tell us you have an untracked file. So this is a file that we haven't told Git anything about yet. It just knows that we created it. So we're in the middle of work. And we're going to pretend someone has just sent us an email that there is a horrible bug in the piece of software that we're working on. So we need to stop all the work that we're currently doing, and we need to go fix that bug. Git and having a branch makes that pretty easy. Because the thing you can do is you can make a work in progress commit. So this is a commit that you'll throw out when you're finished, but it will hold on to the change that you've made, it'll put it into your repository, potentially it'll put it back up to your server if it needed to live for that long. So these commands I actually have in a shorthand command, but I've written them out so that we can kind of see what they're doing. So inside the script that I have called git-whip, it does git add --all, so that takes all the changes that are in the that are currently in the repository and adds them into the index. Git ls files. So ls files is similar to doing regular ls in Unix, except it's doing ls on the files that Git actually knows about. And in this case, I'm doing ls on the deleted files. Because what I'm doing with this command is I want to find any files that I've deleted on disk, that I haven't told Git about them yet. And I want to use git rm to take those files and mark them as deleted. So this is just a small detail. So this is xargs is a utility in Unix that will take a list of things that are piped into it and then turn them into arguments for the command you pass it. So this is going to get me a list of files, and then on each one of them it's going to run git rm, the name of the file. In this case, I don't have any files that I've deleted, so it doesn't have anything to do. And then it creates me a commit message with the name of WIP. do this as an example in local 2. So we go File, Status is on track just like it was before. And then I'm going to use the Get Width shortcut. It runs through, throws out that same error message, lets us know that it's created a commit with one file changed, one insertion. And if I check the status, it lets us know this is still the master branch in this case, but we now have one extra commit. And look at there, we see our one width commit. So, now the fact that this is committed in our, so the detail here is we now have made our working directory clean. There are no uncommitted changes sitting in our working directory. And what that means is we can now change out of our branch into another branch. So, while we're doing this, we have an emergency bug fix. We have something that we have to go and do in the code right now. So, but we've taken all of our work, we've effectively saved it away in a commit in our branch. And now, we go back to the master, because we know that master code is, again, our master code is our main line of development of the software, and we know that's where the bug actually is. So we go back to the master, then we make a new branch for our emergency fix. We'll call it emergency. Our emergency fix is very simple. We add emergency fix to file 1 to file 1. Very exciting. And then we do commit. Now this time we can feed commit the -- all flag, and we'll make it do the same thing that git add -- all was doing before. So it takes all the changes, says, okay, I assume you just want to add everything that's been changed into the commit. It'll add them to the index, and then it'll add them to the commit all in one command. Gives it the message of fixed the emergency. Gives you the same information about what it's doing. We got one file changed, we've inserted one line. We can check. We can see that the working directory is now clean. We've added all of the changes that we've made. It's all of our changes now have a commit. And if we do a log, we see that in our emergency branch, we now have the single commit from our master branch, the emergency commit that we just created, and none of the other commits from our branches, because we have completely ignored them inside of this, and we've been able to do our one fix in isolation. So you can see again, well, it's hard to see it, but trust me when I say it, this number is still the same. So this number for this commit is the same across the master branch, the emergency branch, and branch number 1. So now we've got our emergency fix done. Say we've run our tests locally. Now we have to send it up so that it actually gets back to the main line, gets pushed out to production, gets distributed to whoever is using our software. So we check out the master branch again. And we're going to merge our emergency branch into our master branch. So this is where Git is going to take the new commits that you've created in the emergency branch and add them onto the master branch. Now, in this case, the merge is very simple. It's called a fast forward merge, because all you're doing is you're finding the commonality. The Git looks and says, oh, look, these guys have a common commit, and emergency branch has added more commits onto the end of that. It hasn't modified any commits. It doesn't have a divergent history at any point. So it says, oh, I can just take the new commits from the emergency branch, add them onto the end of the master branch, and I don't need to do anything else. I don't need to report any merges. I don't need to report any conflicts. So it lets you know that it's just doing a fast forward merge. So after we do our merge, we do a git status, and that lets us know again that we're on the master branch. And now our master branch has that one emergency commit that the remote branch doesn't have. So it lets us know that we're ahead of origin master by one commit. And it has the exact same commits as our emergency branch does. So if you compared emergency and master right now, they both look exactly the same. If you went back to this diagram, it would be as if if this node at the very bottom is the end of our master branch, the master branch pointer and the emergency branch pointer are just pointing at the same thing. Oh, I did miss something.